Hey everybody. For this section, we're just going to go through some homework questions, and this section is about functions in several variables. So if you take a look at this example here, notice you have a function of f of x, y, and z. So your function is, you're inputting three different variables here, and so your output would be considered a fourth variable. You can call it some other letter, maybe like w is your output in this case. So for this first one here, all that this is saying is plug in 2 for x, -3 for y, and 4 for z. And then whatever you get as your output is what this function is asking for. So we'll just work this one out really quick. So in the numerator, we have x minus y. And in our denominator, we have y squared plus z squared. So we get 5 on top, and it looks like 9 plus 16 on bottom. So that's going to be 5 over 25, which we can simplify that to 1/5. So let's type that in. So 1 divided by 5. All right, and that's all that requires. So the thing with functions of several variables is a lot of times in real life situations, you have multiple variables that you have to input into a function. Like for example, let's say this function, and I'm just sort of making this up, but it could describe something like temperature at a location on the planet. So your inputs would be location, maybe that could break down into like a longitude and a latitude coordinate, and maybe also the time of day would be an input that you're finding that temperature at. So lots of situations require multiple inputs. So functions of several variables involve things like that. So let's try a different question. Okay, so here's another question. Find and sketch the domain for this function. So whenever you're asked to find the domain of a function, what you actually kind of want to do is think about what's not in the domain, because usually that's easier to figure out. So you think about what kind of restrictions there might be. And in this case, we're taking the natural log of this argument. And so you want to say, well, what would cause a problem if I take the natural log of it? What numbers, if I plug them in for x and y, would cause this problem? And so with any log functions, the argument cannot be 0 or negative. And so you basically say it has to be greater than 0. So all you're going to do on this one, let's see, out of our options, it looks like D. Okay, so x squared plus y squared minus 81 just has to be greater than 0. Okay, and then now it also says to sketch this domain. So let's see what we have to do for that. So let's just write that here. We have x squared plus y squared. And then I'm going to go ahead and say that's greater than 81 if I just add 81 to both sides. And so this is a circle with radius 9 because 81 is 9 squared. But it's values for x and y that are greater than that circle. And so it's got to be either A or B in our answer choices here. And first of all, if you think about it really quick, if you knew this from the past or if you didn't, whenever you have just a greater than or less than symbol and no equal sign, we technically can't include the boundary. And so by just knowing that, it has to be B because it's dashed. It's a dashed circle line. If it was solid like A, we would be including the boundary, so we would have an equal bar in our inequality. But besides that fact, it's the outside of the circle because we want greater than the circle. We want outside of that radius 9, so everything outside of that. All right, so now let's move on and try something else. So on this next one, it's going to be a similar process. Find the domain, and so you ask yourself what would cause a problem if I plug it in for x and y. And in this case, we have a square root, so we can't take the square root of something negative and get a real answer out. So we have to make sure that the radicand is 0 or more, so it's got to be part C here. And then you just basically say this radicand has to be 0 or greater. Now I'm going to break this down because it's going to help with the next part, the sketching. So notice that your radicand can factor. The x squared minus 25 is x minus 5 times x plus 5. And then the y squared minus 9 is y minus 3 times y plus 3. And so let's see what that tells us for the graph. Now look at our choices for the graphs. Now what you have to consider here is all of these numerical values that would make this equal 0. So if x equaled 5, if x was negative 5, y was 3, and y was negative 3, all of these would equal 0. So that's part of the boundary. So let me just put that here. So if x is 5 or negative 5, y is 3 or negative 3. And so you have lines. So these first two, x equals some value, these are vertical lines. And then the second two, y equals some values, are horizontal lines. So by that choice, it has to be B or C. Now, what you would want to do to figure out which regions, because you do have this inequality symbol, which regions kind of cut off by those lines would satisfy this domain or this inequality right here, is you just sort of test some numbers. So I'm going to just pick a few and then we'll pick our answer. So let's say I want to try the origin. I want to see, does the origin satisfy this inequality? Does it make this radicand positive or 0 so that I can take the square root and get a real number answer? So if you try it in either version, you can plug it in here or all the way into the original. If you plug in 0, 0, look what you're going to get out. You're going to get square root of negative 25 times negative 9, which is positive. And so that one's going to work. You can also plug it into the inequality that we have right here, and it will be greater than 0. And so 0, 0 works, meaning that it has to be, just by our choices here, B and C, it has to be B, because 0, 0 is right here, and it's shaded in, meaning we can use that part of the region. And you can double check. You can try some other values, and you'll find out whether they work or not. Just for example, let's say we picked up here 0, 10. It won't work. So notice it's not shaded in. It's not going to satisfy our original function or our domain here. So if we plug in 0, 10, and this time I'll plug it in right here to this domain that we came up with. So if I plug in 0 for x and 10 for y, I'm going to get negative 5 times 5. That's the x factors. And then 10 minus 3 is 7. And then 10 plus 3 is 13. It doesn't even matter what this number is, just as long as you notice that this is a negative number, because it's a negative times 3 positives. So it's definitely less than or equal to 0. It's not greater than. So the next question here, it has to do with something called the level curve. So let me explain a little bit about that. Now, a level curve is similar to a contour curve. And so let's go to the book for that to show you something pretty interesting. So if you were to consider like traveling around mountains or hills, if you were walking sort of around it, so if you kind of zoom in on this picture here, let's see if I can do that. So if I can walk and not change my elevation, so let's kind of say right over here, see this white line here? If I could actually travel around this hill and stay on that white line, I wouldn't be changing my elevation. That's what's considered a contour curve. And then if you take all of the contour curves and you project them onto a plane, specifically the domain, that's what's called a level curve. And so let's look at a different page to show you. Okay, so if you have, for example, this is your function, the light green. Here's what I was saying about the contour curve. If you were traveling around at the same elevation, the curve around your function or your surface. And if you take that curve and you project it down into the domain, in this case the xy plane, that's considered a level curve. So here's a map of an actual place. It's Mount Washington in New Hampshire. And this is the contour curves, but they're projected into this 2D space, so you can think of them as level curves. But it's letting you know about if you were to travel at the same elevation around the mountain. So let's go back now and take a look at the homework. So for level curves, you take your function and you set it equal to constants. And then that way you find all the level curves at that particular elevation. So this example, this question is saying to specifically look at when z is these values from negative 2 to 2. And so all you do is you take your z and you set it equal to negative 2, negative 1, 0, 1, and 2. So let's just do a couple of them. Let's go with negative 2. So negative 2 equals 4x minus 2y. And then just think about what shape this would be if I graph this. This is a line. If it's not quite clear, I'll show you. If we divide by negative 2, we're going to get 1 equals negative 2x plus y. And then that's y equals 2x plus 1. So it's just a line with y-intercept 1 and a slope of 2. So it's got to be line. So right away it's not answer B. And so let's just plug in another one. Let's go ahead and plug in 0. So 0 equals 4x minus 2y. And so if we simplify that a little bit, we're going to get 2x equals negative y. Actually, negative 2x equals negative y. And so this is just y equals 2x. And so that one's going to be, if we kind of zoom in here, notice this is a positive slope 2. This was a positive slope 2. So let's zoom in on C and see if that's correct. So if we plug in 0, 0, we go through the origin, and then we would go up 2 and run 1. So that looks like that's pretty accurate in this middle line here. So let's compare that to this part A, because they look pretty similar. That goes through 0, 0 and up 2 and over 1 as well. Okay, so let's see if there's a difference here in these two. Part A and part C. From here, they look really the same to me. Let me pop them out one more time. Okay, and we have this line going from negative 2 up 2 and over 1. Okay, let's see down here. Negative 2 up 2 and over 1. I think these are identical, so A or C should be fine. They're both the same answer. All right, this might be an error with the program, so let's go with C. There it is. All right. All right, for this next one, we're going to complete these parts A through F. And so first, let's find the domain. And if you notice, there's no real restrictions here because any real numbers we plug in, we're going to get real numbers out. So the domain is all real numbers, but because we're inputting both x's and y's, it's all real numbers in 2 dimensions, which you can say is R2 or the xy plane. So for the range, we have to think about what kind of numbers would come out based on our domain. So if we plug in any real number in for x and y, what kind of numbers come out? And is there any kind of restriction on what comes out? Well, let's see. If we plug in positive numbers for x and y, we're going to get out positive numbers. If we plug in 0, we're going to get 0. But if we plug in negative numbers, when we square them, they're going to turn positive. So no matter what numbers we plug in for x and y, this function will actually never be negative. So there is a slight restriction on the range as far as what comes out. Not all real numbers will come out because nothing negative will come out of this function. So this range is going to be, so notice it says interval notation. The smallest number we're ever going to get out is 0. So we can say it can equal 0, so we use a bracket, and anything greater than that, so it can go to infinity. And you always use parentheses with infinity because you technically can't equal it. So for this next part, for the functions level curves, remember what we talked about. It's when your curve, you're only staying at a specific elevation on that surface. And so you can set your function equal to specific constant values. So in our case, I'll just say C equals 9x squared plus 16y squared. And you can pick a few numbers to see what kind of shapes your level curves will look like. Let's just go ahead and plug in 1 for C, and then just think about what shape this would be. And this one here, if you think about it, you have x squared plus y squared, but the coefficients are different. And so you're going to end up having an ellipse. This is an equation for an ellipse. And if you pick another number for this to equal, it's going to be the same thing. If you divide out the 9 and the 16, this is still an ellipse. Now, is all of the level curves going to look like this? Almost all of them, but what happens when we plug in 0? Take a look. If I set my function equal to 0 and I try to solve this one, the only time that this is true, that when I'm going to add this and get 0, and you could try to solve it, it's going to be when x and y are both 0. And that's because if I'm going to add two things that are positive, notice when I square anything here, it turns positive if it was negative to begin with. So if I add two things that are positive and the result is 0 somehow, the only way that this is ever going to be true is if I plugged in 0 in the first place. So all of your level curves are going to look like ellipses other than when your elevation is 0. And so at that one, you just have a single point at 0, 0. So if we look at our choices here, we have for our function equal to 0, the level curve, part A says it's the x and y axis, part B says it's the origin, so that's got to be right. Let's just check the rest. Anytime we don't set this equal to 0, we get ellipses, which was correct. All right. So then part D, find the boundary of the function's domain. Now, let's go to the book really quick. Okay, so in our book, we have some information here about boundary points, and it's fairly intuitive what you might think a boundary point is. It's a point on the boundary, but there's a pretty mathy definition for it. Basically, it's considered a boundary point if you can draw a disk around it, and your open disk, like this little circle here, part of it's inside your region. The region is, think of it like the domain. Part of it's inside the region, and then part of it's outside the region. So that's the more technical definition for the boundary point. And then the interior point, again, it's pretty intuitive. It's a point inside the domain or the region, but the more mathy definition is that it's an interior point if you can draw an open disk around it, and that disk is also inside the region or the domain. So those are boundary points and interior points. And why we care about those definitions is because it leads to whether or not our region or domain is closed or open. And so right here, a region is open if it consists entirely of its interior points. So if you can basically draw these open disks around every single point and still be within the region, it's considered open. And then it's closed if it contains its boundary points. So technically, it's a little bit complicated as far as definitions, but intuitively, it makes a whole lot of sense if you just think about something's open if there's nothing closing around all the points. And we denote that a lot with like dashed lines. It's closed if you can create like a border around it. Now, I'll show you with this example. It gets a little interesting because it's going to be open and closed. So I'll explain that in just a minute. So it's technically open if it only consists of interior points and closed if it contains its boundary points. Now, let me talk about one more thing down here. A region is considered a bounded region if it lies inside a disk of finite radius. Pretty much that means if you can draw a circle around your region and it's an finite circle, not like a circle that goes on forever. If you can enclose your region in a circle, then it's considered bounded. Otherwise, it's considered unbounded. So taking a look back at our homework here, for the boundary of the function, find the boundary of the function's domain. So the domain, if we come back right here, the domain was the entire xy plane. So the boundary of it, well, it's all numbers for x and all numbers for y. So there's actually no boundary points in this one. Then determine if the domain is open or closed or neither. And so this one's a little tricky whenever we're dealing with all of R2, all of the real numbers in 2 dimensions. So real quick, I'm saying R2, but we write it like this. It's just the real numbers in 2 dimensions. This is actually both open and closed. It's both open and closed, and here's why. It's open because if you think about it, the real numbers are infinite if I consider all my x numbers and all my y numbers. So I can kind of go in all directions with the x numbers and all directions with the y numbers, and every point in here would be an interior point, okay, to this R2 space. That's the open part of it. But at the same time, it's also sort of considered closed because this is a closed set as far as real numbers. So it contains all real numbers in 2 dimensions. So it's closed in the sense that it contains all of its boundary points as well. It is a little weird to think about, but it's both open and closed. So even though there's not like edges of the real space, R2, what you want to think about is that can you think of any real numbers that would exist outside of R2? No. So it contains all of itself. So that's the closed part. Decide if the domain is bounded or unbounded. So this is the nice one. If you can draw a circle around it and enclose it, it's bounded. We can't. This goes on forever in all these directions, so it's definitely unbounded. All right, let's try another one like that. So given this function, answer the following questions, starting with the domain. So in this one, the domain, think about what would cause a problem here. Well, a couple of things would cause a problem. Anytime we would divide by 0 would be an issue. So this denominator cannot be 0. So square root of 4 minus x squared minus y squared cannot be 0 because it's the denominator. But then also we have a square root, which we don't want to take any square roots of anything negative, so we have to make sure that that radicand is greater than or equal to 0. So if we put these two things together, we just say that this radicand, 4 minus x squared minus y squared, has to be greater than 0. And so if we just make this look a little more friendly, let's see, I'm going to subtract 4 from both sides, so let's just do this in steps. Let's make it look a little nicer. Minus x squared minus y squared, and then is greater than -4. And if we divide out a -1, we're going to get x squared plus y squared is less than 4. And so this is an equation of a circle with radius 2. And so if we look at our choices for the domain, it's going to be the set of all points that satisfy x and y as long as it's less than 4. So notice, careful, it's not C because there's an equal bar, so it's D. And there's no equal bar because we can't equal 0 because this is in the denominator. Okay, so next, the range. What kind of numbers come out of this function? So we know that we're not going to plug in anything outside of the domain that we just figured out. Think about what kind of numbers come out of this function. We have 1 over a square root. So no matter what numbers we plug into the square root, it's going to be positive. Even if we plug in numbers like 0, we're never going to get 0 in bottom. We excluded that from the domain. So no matter what we plug in, this is going to be 1 over something positive. So let's see what our choices are for our range. So we have that z is greater than 0 but less than or equal to 1/2, greater than or equal to 1/2, greater than or equal to 2, and between 0 and 2. So let's see if we can narrow down the fact that all we said so far was it was positive. So think about if you plug in 0 for x and y, you're going to get square root of 4 minus 0 minus 0. So that's square root of 4, not 2, square root of 4, which is 2. So 1/2. Now if I plug in something positive or negative, I'm going to just end up subtracting that from 4. So let me show you what I mean. Let's pick 1, comma 1. Let's just plug in a point for x and y. So this is going to be square root 4 minus 1 squared minus 1 squared. So this is going to be 1 over square root of 2. So 1 over square root 2 is actually greater than 1/2. Okay, for this next part, we're going to choose the description for the level curves. So that's where we're going to take our function and set it equal to constants. So we have c over, or equals 1 over our square root, 4 minus x squared minus y squared. And we can just plug in some numbers and see what happens. Let's just try 1. So if I set this equal to 1, and then I try to make this look kind of more familiar, I'll be able to figure out what these level curves look like. So let's multiply both sides of this equation by the square root. And at the same time, I'm going to square both sides. So this is going to be 4 minus x squared minus y squared equals 1 squared. And then if we move stuff around, this is going to be 4. If I bring the 1 to the other side, minus 1 equals x squared plus y squared if I bring those to the right side. And so this just looks like a circle. So this is 3 equals x squared plus y squared. And so that's just one level curve. It's a circle with radius square root of 3. And I can keep doing this. And what I would find is that I'd be subtracting my c value. So whatever I chose for c, which is this number here, I'd end up subtracting it from 4. So our circle is going to always have a radius of 4 minus our choice for c. And so if our circle always equals the radius squared, that means that it's always going to be smaller than radius 2. So this is actually going to be part D, circles with the radius less than 2. It's never actually going to equal radius 2 because if I plug in a 0 for what our function equals, this is really never going to be 0, and therefore the radius would never actually equal 2. Going to be just strictly less than 2. So let me show you what that looks like really quick with the graph. So here's your function in 3 dimensions. So it's this surface, and if you were to kind of look at it from above, you would see the level curves. And so notice that they are circles where the radius is less than 2. So for part D, the description of the boundary of the domain, if we go back to what we figured out the domain to be, it was the circles with the radius less than 2. And so the boundary would be when this circle equals 4, or the radius equaled 2 squared. The boundary is exactly the edge of this domain. So in this case, it would be this circle. Then the description of the domain, is it open or closed or neither or both? Well, if we kind of go back up here to what our domain looked like, if you can picture this, it is pretty much what we looked at on the graph with the level curves. It's a circle with radius less than or equal to 2, just less than 2. However, it's not equal to 2. Notice we didn't conclude that there was an equal bar because the domain, remember the denominator part, it couldn't be 0. So there was no equal bar. So basically, if I were to draw this better, I would have a dashed circle because I technically don't include the boundaries of this circle. And so with that in mind, then everything in here would be an interior point, or just think of the fact that this is like open dashes. That's a faster way to think about it. So this is an open region, and nothing about it is also closed in this case. So it's not a tricky one. Is the domain bounded or unbounded? So remember what that means. If I can draw a circle with a finite radius around it, it's bounded. And I definitely can. If I just take any circle that's bigger than radius 2, I can draw it around there. So that one's bounded. So let's take a look now at some functions and their surfaces and then their associated level curves. And so this function, 4x squared plus 4y squared, if we think about what that would look like, if you kind of think back to what you know about some surfaces and their equations, this is actually the equation of an elliptical paraboloid. So you kind of want to reference what you've learned about surfaces in order to sketch these functions fairly quickly. Or you can always plug in some points and plot them and just sort of do a quick sketching, and you'll figure out that it's going to be this one here. So now, let's see, we're asked about the level curves. And so if I were to think about staying at a specific elevation, let's kind of make this one bigger here. If I were to stay at a specific elevation on this surface and just sort of travel around, and I just do that a few times, what would that look like? And so intuitively, you might kind of already have a guess in mind, but let me show you really quick with a drawing. So I'll just sort of draw this from the sideways view. So our surface kind of looks like a bowl like this. And if I were to take just one like slice out of it at a specific elevation, and I were to draw that onto the XY plane here, then that would look like a circle. And I can do that again and again. And if I go higher up on the surface, it would just be a circle with a bigger radius. So hopefully you were thinking that it was A. Okay, now let's try kind of the opposite. We're given the level curves, and we have to match it with the surface that it came from. So this is the projected level curves onto the domain or the XY plane from a surface. And so you want to say, well, what surface would give me those level curves? Right away, A cannot be correct. It doesn't seem like it would match up at all. It looks like B or C, but if we sort of just pay some attention to the details, that there's like these 4 loops here, that would be where there would be like either mountains or valleys. So there has to be 4 of them. The answer here has to be part B, and that's because if you notice closely, there's 2 mountain peaks, and then there's actually 2 valleys, one sort of to the back that's hidden from our view. But then everything else is at the same level or elevation, and so that's what these level curves would represent. All right, let's try one more problem here. Find an equation for the level curve that passes through this given point. So this function, remember, for level curves, we set our function equal to a constant value. And so this is c equals 25 minus x squared minus y squared. We are told that this level curve has to pass through a specific point, and that point is given as an ordered pair x comma y. So all we really have to do here is just plug in what x and y should equal on this specific level curve, and then we're going to end up finding what c should have been, or is. So that's square root of 3 squared minus square root of 3 squared, because both x and y happen to be the same number. And then we get 25 minus 3 minus 3. So that's going to be 19. And so c is 19. And so our level curve that passes through this point is 19 equals 25 minus x squared minus y squared. And I can probably type it in like that, but I'm going to just make it look a little nicer. I'm going to add x squared and y squared to the other side. And at the same time, I'm going to go ahead and subtract 19. So that equals 6. So let's type that in. So we have x squared plus y squared equals 6. And there it is. All right, so that's it for this section.